So I want to do problem number 12 off of page 292 of our text. The Ethan Allen tour boat capsized and sank in Lake George, New York, and 20 of the 47 passengers drowned. Based on a 1960 assumption of a mean weight of 140 pounds for passengers, the boat was rated to carry 50 passengers. After the boat sank, New York State changed the assumed mean weight from 140 to 174 pounds. Given that the boat was rated for 50 passengers, with an assumed mean of 140 pounds, the boat had a passenger load limit of 7,000 pounds. And so that's just telling us something we could have calculated on our own, that with 50 people at 140 pounds apiece, we have that weight limit of 7,000 pounds. Assume that the boat is loaded with 50 male passengers. This is another worst case scenario. On average, men tend to weigh more, so if we have only men on there, we're kind of assuming the heaviest possible sample we could get. And assume that weights of men are normally distributed with a mean of 189 pounds and a standard deviation of 39 pounds. So I've already drawn a Bell distribution here, that is the distribution of men's weights based on data that appears in the back of our textbook. Find the probability that the boat is overloaded because the 50 male passengers have a mean weight that is greater than 140 pounds. So right away in part A, this isn't actually the distribution I need to use, because I need to talk about the distribution of sample means. The central limit theorem definitely applies because my original population is normally distributed, but even if it wasn't, if I look at the sample size here of 50, that's over 30. So even if this was not a normal distribution, the central limit theorem would still apply. The mean of all of the sample means is equal to the population mean. And the standard deviation is the old standard deviation divided by the square root of the sample size. So 39 divided by the square root of 50, and these are both in pounds. And then I'm asked a probability question. Find the probability that the boat is overloaded because the 50 male passengers have a mean weight that is greater than 140 pounds. All right, well, this is another normal CDF problem where we start at 140 and need to shade forever, and this is where I like to use a 10 to the 99th. It's assuredly so far away from the mean that all of the data, almost all of the data lives there. Since we're talking about weights here, no one's weight could possibly be that high, so actually all of the data will lie in that interval. The mean is 189 and the standard deviation 39 over root 50. Get into the distribution menu by hitting second in vars, choose normal CDF. And we're just going to type in what we've written down there. And we get a probability so close to 1 that the calculator actually rounds it to 1. With 50 people on that tour boat, it is almost certain to sink. Now we know this can't actually be a probability of 1 because there's some unshaded region over here. Every once in a while I like to be kind of sneaky and like write a 1 minus saying that we know it's a little bit less than 1. But this is a super dangerous situation. The tour boat is almost certain to be overloaded and be in danger of sinking with 50 people on it. All right, part B tells us the boat was wisely later redesigned. Or re-rated. The boat was later rated to carry only 14 passengers, and the load limit was changed to 2,436 pounds. And again, this is just changing the information that is given, right? Lowering the weight limit, limiting the number of passengers. If 14 passengers are all males, again, assuming that worst case scenario, find the probability that the boat is overloaded because of their mean weight being greater than 174 pounds. So their total weight is greater than that of the maximum capacity. Well, again, if we look at that load limit, 2,436 pounds divided by the 14 passengers, that's where we're getting that 174 from. Well, again, I'm looking at the distribution of sample means. This time, I'm glad the original population was normally distributed so that I get to use the central limit theorem. The mean of all the means. still 189 pounds. The standard deviation is now 39 divided by this smaller sample size of 14, root 14, excuse me. Sample size is 14, but I divide by the square root of the sample size. And now I need to know the probability of getting a sample with a mean weight of 174 or more. All right, well, normal CDF takes in that left-hand endpoint, goes all the way over forever, and then I type in a mean, 189, and then this new standard deviation, 39 divided by root 14. So, go into the distribution menu again. And we get a probability of 0.9249. I'm rounding to 4 decimal places today. We typically round probabilities to 3. But either way, that's over a 92% chance that even with this new restriction, this boat still is overloaded and is unsafe. Do the new ratings appear to be safe when the boat is loaded with 14 male passengers? No. There's a 92% chance that we've overloaded the boat again, and that's another unsafe situation. So that weight limit needs dropped even more, though at this point, if you thought you'd built a boat for 50 people and then you cut it down to 14 people, I think it actually might be time to redesign the boat.